As artificial intelligence moves beyond simple text generation into the realm of complex reasoning and real-world action, the engineering focus is shifting. We are moving away from stateless, isolated interactions towards stateful, autonomous agency. The foundational engine for this autonomy is the ReACT loop, short for reason plus act. It creates a recursive cycle where a model thinks through a problem, takes an action, and observes the result. This chart shows a standard ReACT loop in operation. While it appears dynamic, it is subject to a mathematical reality known as the probability tax. Every time the model makes a decision or calls a tool, there is a specific probability that the step will succeed. If we stretch this loop into a 5-step sequence where each individual action has a high 90% success rate, the overall reliability of the chain is the product of those individual probabilities. By step 5, the total success rate has dropped to 59%. At 10 steps, the mathematical decay is even more severe. The reliability of the entire system locks in at just 34%. Because errors in these feedback loops compound, a single logical slip early on can lead the system down an inescapable path of flawed reasoning. In high-stakes environments, this makes simple prompt engineering insufficient for production. Reliability in autonomous systems is a structural engineering requirement. It requires wrapping the model in a governed architectural layer designed to manage the scarcity of context and the enforcement of policy, the Context OS. To build this system, we have to treat the model's context window as a finite workspace. Measured in tokens, it acts as the model's active RAM, a high-value but strictly limited resource. This diagram represents a context window filling with data. When a hallucination or error enters this workspace, the red blocks shown here, it is reused as a fact. This is context poisoning, where a single error compounds until it crowds out valid information. Long-running sessions also face context distraction. As the conversation grows, the agent's core instructions are buried under thousands of tokens of raw tool outputs, making the model over-focus on past patterns rather than the current goal. Context engineering addresses this by managing the deliberate transfer of information between the short-term working context and long-term external storage. Effective memory uses a multi-tier pyramid, a message buffer for dialogue, core memory for pinned data, recall memory for history, and archival memory for massive databases. A background process summarizes top-tier interactions into episodic highlights in the recall tier. This background consolidation preserves the precision of recent instructions while preventing the model from being burdened by irrelevant history. By treating the context window as a dynamically compiled and versioned asset, engineers can maintain the continuity of an agent without triggering the failure modes of context exhaustion. The Context OS functions as a decision harness, organizing the agent's lifecycle into 3 interconnected architectural planes. The foundational layer is the context plane. It performs context compilation, assembling relevant information and resolving conflicting data from different systems, like an ERP and a CRM, into a single validated truth. This pre-processing ensures that every agent in a system reasons on the same validated data, which can reduce token costs by up to 60% by eliminating redundant retrieval and noise. Above that is the control plane, which uses a dual-gate architecture. Gate 1 evaluates policies before reasoning starts, restricting the agent's visibility to only authorized data. Gate 2 evaluates the agent's proposed action before it executes.
This Gate 2 check ensures that actions adhere to deterministic constraints, such as spending limits or safety rules. If an action violates a policy, the system can modify or block it before any real-world side effects occur. The final layer is the decision plane. It records the full lineage of the interaction, capturing the exact context, the policies evaluated, and the authority verified into an immutable decision trace. Within this system, natural language is replaced by rigid typed schemas for agent-to-agent communication and tool use. This prevents the model from hallucinating capabilities it doesn't have. To integrate safely, tools are designed to be idempotent, meaning they can be retried without unintended side effects, and they return context-rich errors that explain to the agent how to fix a failed step. These 3 planes together replace the unpredictability of prompt-based instructions with a structural framework that makes non-compliance architecturally difficult. As tasks scale, single-agent architectures often hit a bottleneck. A model loses precision as it takes on too many responsibilities, leading to tool confusion and context exhaustion. Multi-agent orchestration solves this by distributing work. This diagram shows an orchestrator-worker pattern, where a central supervisor node decomposes a goal and routes specific subtasks to specialized worker nodes. These agents collaborate through a shared information environment using the Model Context Protocol, allowing them to access centralized data while keeping their own working memory focused and uncluttered. While orchestration distributes the workload, it does not automatically fix the probability taxed. To improve the success rate of individual nodes, engineers use the reflection pattern. In this pattern, one agent generates an output, and a separate reviewer agent in a fresh session critiques it. This separation ensures the critique is not biased by the original reasoning assumptions. Combining multi-agent routing with these reflection checkpoints allows the system to scale to complex workflows while maintaining structural control over reliability. Traditional observability, focused on technical signals like latency and uptime, is insufficient here. An agent might technically complete a task without errors while still making a poor business decision. We have to move from outcome evaluation to trajectory evaluation. This comparison shows how two identical results can hide different behaviors. On the right, the agent reached the correct answer, but its trajectory was highly inefficient and bypassed security protocols. Analyzing the full execution trajectory, the reasoning steps, and the tool calls is the only way to detect regressions in non-deterministic systems. Because agents operate in complex, unpredictable environments, engineers are adopting a methodology where agents are used to research and prototype the requirements they will eventually implement. This is the research, specify, implement pipeline. It creates a disciplined sequence for agentic development. During the research phase, the agent analyzes the codebase and documentation to generate a detailed findings document. In the specify phase, those findings are converted into a rigid technical contract. This acts as the formal bridge between human intent and AI execution. Finally, the implementation happens in a fresh agent session, devoid of any conversational noise. This ensures the agent is biased only by the formal specification, not a long, messy history. In this paradigm, the role of the engineer is to architect the systems, the memory,